Hello, this is the fourth video in a series I'm calling Transformations of Random Variables, and here we're going to look at, I'm going to call the Multivariate Cdf Technique. In general, transformations work with, you have a random variable x and it's multivariate, say k dimensions, and the domain we're going to call S, and there's a set in S that's mapped to through the function h to a set B in T, where T is the I guess it'd be the image of x or h, or the domain of y, which we call y of h of x, and they're all vectors, so this could be m dimensions different than the k dimensions there. And then there's a pre-image associated with the mapping of h. The theorem that we talked about earlier, this is exactly the same as the univariate case, but it's the multivariate case. So let x be this vector, be a random vector, and let the transformation of h go from s to t be measurable, which means this vector y is a random vector also. And the distribution of p of x of this random variable p of y of this random variable y, random vector y, is determined by the distribution p of x of the random vector x. And it can be, it's for all b in the domain T, py of b is equal to px of a, which says that the probability that y is in b is equal to the probability that x is in a, where a is the pre-image of b. And so, also as in the univariate case, the distribution of y, py of the random vector y, is uniquely determined by its distribution function. So if we set b to be all values less than or equal to some random or some constant vector little y, then we can determine that CDF, based upon this CDF, and then we can take the derivatives of it if needed, and we can find the PDF of that variable. So here's a quick example. Let's let x1 and x2 be independent, identically distributed, uniform random variables from alpha to beta. We want to find the CDF of y and the density, or the density of y, of the random variable y equals x1 plus x2. So since x1 and x2 are IID, then their density is the product of the univariate densities, which is 1 over beta minus alpha squared. Now to find the CDF of y, we write it here, which is the probability that y is less than little y. Well, then if we substitute in x1, x2, we get this. Now to go from here to here, we use what's called LOTUS, the law of the unconscious statistician. And if you search in my videos called LOTUS, that explains that we, even though this is a function of x1 and x2, we really only need to have the joint density of x1 and x2, but then integrate it, or sum if they're discrete, over the region that satisfies this. And again, you can look at LOTUS to maybe get a little better understanding of how we can jump from here to here. But what that means is, so we'll ignore this for a second. So we have x1 and x2, and then this would be the region. They're uniform from alpha to beta, and the density over the top it's constant, right? So to find probabilities in this region, we just need to find the area of this square and then take it times the density, which is constant. So now we have to find regions that are satisfied by this right here, x1 plus x2 less or equal to y. And then the way I think about it is, this is the abscissa and the ordinate, so I like to transform this into this. So x2 minus less than or equal to y minus x1. Well, this creates a line of slope minus 1 And so varies like this, up and down, depending upon x1 and x2. And then you can kind of see that if we're in this region, that we have to find the area of this lower triangle plus that sliver. Here it's just a lower triangle, and to be less than this is 0, right? Because we're not in the region anymore. So what we do is we break it up into, I'm gonna call it, well, it's technically 4, 1, 2, 3, and 4 regions. But this is 0, and to be, a value here less, it would be 1. So we're going to focus on these two regions here. Now this line ends up, it ends up being y less than or equal to alpha plus beta. Okay, you can see that right. Well, that's right here. So if you plug in, so like x1 is beta and x2 is alpha, you plug them in and then you get this equation. And then to be less than here is the y less than or equal to 2 alpha, and you can do that. So to be in between these is this region here. Y is between 2 alpha and alpha plus beta. So let's look at these regions here. Like we said, to be less than y equals 2 alpha is 0, because there's no chance of it happening because we have to be in this region. Then to be in the second region, which is between y between these values, which means that line is somewhere between those two lines. So if we pick an arbitrary spot, and then we want to be less than that, the probability is really the area of that square times the density, which is 1 over beta minus alpha. So this is the CDF of a random spot picked between these. So if we just need to find that area where the area A is below the line. And if you can kind of do the mental math, and then it ends up being the area is 1/2 the base times the height, and then you can see that the base and the height are the same, and it ends up being y minus 2 alpha. And so there's the area of that little triangle, and so you divide it by that, and that's the CDF. So to be in this region, y has to be between alpha plus beta and less than 2 beta. So now to pick an arbitrary spot, say y, little y in here, we need the CDF is actually the area below this, but sometimes it's easier to take the area of the whole minus that little piece there, and then what's left over is the area we're looking for, and that's what we do. So this is the CDF, but now we need to find the area. Well, the area, this is beta minus alpha in length, so the area is that squared. So the area below this is the area of the square minus the area of being above that line, which ends up being 1/2 2 beta minus y. And you see this because this length here is the same as that length, and that's why it ends up being squared, and it's 2 beta minus y. So what does that mean? That means that we have this relationship here, that our CDF is 0 if we're less than this, it's this value if we're between, and it's 1 minus this if we're here, and it's 1 if we're beyond it. Now, a graph of this looks like this, okay? So this first piece here actually is this graph that does this, and then it ends up going up like this. But it's restricted between 2 alpha and alpha plus beta, so it's just this. And then this lower piece here ends up being, it looks like this. But we have to restrict it between these values, and so it actually touches and then goes up, you know, to 1 because it's a CDF, and it goes to 0 over here. Now to find the PDF, what we do is we take the derivative of the CDF, and then so the derivative of each of these ends up being these between those values, and if we plot that, it looks like this triangle distribution. So between 2 alpha and alpha plus beta, we get this, which the height is 1 over beta minus alpha, and then it comes down to 0. And if you integrate that, it is 1. Okay, well, that's all I have for this video. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks, bye.